Welcome. We are modeling the grain boundary grooving problem. So, we have seen the free energy, we have seen the initial microstructure that we need to construct, and we have seen the evolution equations. So, here is a octave script that does this problem. So, as usual we start with clear all CLC, CLF. So, to clear everything from the memory figure and so on. More is off, so that when the microstructure becomes available it will be immediately plotted. We define this function xi, xi has E1, E2, two values, and we saw that it is eta 1 squared or phi 1 squared by 4 minus phi 1 squared by 2. So, that is why it is 0.25 and 0.5, and similarly phi 2 squared by 4 minus phi 2 squared by 2 plus 2 phi 1 squared phi 2 squared plus 0.25. So, this is what we defined the xi function as. So, that is what I have implemented. Now, when we take the variational derivative with respect to phi 1 or phi 2, then we also need the variation the derivative of this function with respect to either phi 1 or phi 2, but this function is symmetric in phi 1 and phi 2. So, we can manage to do the calculation with just one function. So, this is what this xi prime basically is. So, if you differentiate this, for example, this is power 4. So, 4 will come, 4 times 0.25 is going to become 1, and this is E1 cube. So, that is this minus, similarly 2 will come, that is 1 and E1 plus in this case. So, E1 squared, so that will become 4 E1 E2 squared, and if you differentiate with respect to E2, you have to just flip the variables here. You have to call this as E2 and this as E1, then you will get E2 cube minus E2 plus 4 E2 E1 squared. So, that way this function can do both the derivatives. Then I have defined the kappa c, kappa phi 1, kappa phi 2. Like I said, kappa c is 1, kappa phi 1, phi 2 are 1/3, and the constants a, b, z, they are all 1, and we are going to do it on a 64 by 64 mesh with the dx as 1. So, I first need to define the three variables c, phi 1, phi 2. So, they are all initially assumed to be 0. Then I go to the each point in the domain, and if the first quarter or the fourth quarter, if I am there, then I am going to make C to be 1, because that is where the solid is. The central half is basically the vapor, where C will continue to be 0, phi 1, phi 2 will continue to be 0. So, wherever this C is 1 now, half of it I will assume phi 1 is 1, and the other half I will assume phi 2 to be 1. Okay. So, if you end all these if conditions and end the for loop, you basically have a microstructure in which the central half is vapor, and the first quarter and the last quarter are basically the solid. In the solid there are two grains, one half is grain 1, the other half is grain 2 with periodic boundary condition, then you have 3 grain boundaries that are available. Okay. So, this is the initial condition. Of course, we are going to plot it using mesh command. It is sufficient just to look at the composition profile, because wherever composition profile is 1, the phi is going to be 1, either phi 1 or phi 2. Wherever it is 0, phis are also going to be 0. So, if you just can plot composition, you can look at the structure. So, that is what we are going to do. And view 2 is to look down upon the microstructure. So, it is perpendicular or the projection of the surface of composition onto the plane, and pos 0 is to make sure that it goes to the next figure when the plotting happens. Okay. So, of course, we have to define the periodic boundary condition, because we are going to use the spectral technique. So, half n and del k, all those have to be defined. I have not defined the L1, L2 and m, the mobility and the relaxation parameters, because they are all 1. So, I have not explicitly introduced them here, but one can introduce them and make them equal to 1, and you will get the same results. So, these are the time loops. So, first time loop runs from 1 to 50, The inner loop is to make sure that after every 2 time steps we plot the microstructure. So, that is why that is there. And then we start the JK loop, which is for every mesh point, and I have to define a GC, and you can see GC is nothing but 2 AC 1 minus C into 1 minus 2 C plus 2 BC times this xi function minus 2 times z times 1 minus T sin C times the xi function, and then you have okay, I think I have made a mistake here. This should be xi function. Sorry, there is no xi function. So, 2 z 1 minus T times, because it is phi 1 squared phi 2 square plus phi 2 squared. So, it is phi 1 squared plus phi 2 squared. So, that is the GFC, and G phi 1 and G phi 2 you can see. So, the first one A C squared 1 minus C whole squared does not have any phi term. So, that does not appear. B C squared and then xi prime, this is differentiation with respect to phi 1. So, phi 1 is first and phi 2 is next, plus 2 z 1 minus C whole squared times phi 1. Similarly, phi 2 will be B C squared xi prime, but with respect to phi 2. So, phi 2 is first and phi 1 is next, and 2 z 1 minus C squared times phi 2. So, this is the basically the G functions. Once I have the G function, I Fourier transform composition and the phi 1 phi 2 to the Fourier space, and the order parameters are also Fourier transformed, and then we implement the periodic boundary condition here and we evolve. So, the C evolution is by the Korn-Hilliard equation. So, that is why there is a K4 and K2 here, and the phi 1 phi 2 evolution is Allen-Korn. So, there is no K2 here and there is a K2 in the denominator instead of K4. So, once you do this, of course, after every time this is done, you need to take C phi 1 phi 2 to the real space, so that the G's can be calculated in real space and then they can be Fourier transformed for the next step. And after every one of these 2 steps, it is going to plot the composition profile, and then the final end is for the complete time loop. So, this is a code in which we have now implemented the equation that we have seen. So, we have a free energy in terms of C phi 1 phi 2, and we have written down the evolution equation for them, and we have taken the appropriate boundary condition. So, now if we run this code, we will get the microstructure to groove. Okay. So, octave, and then I say source grain boundary grooving dot OCT. Okay. So, you can see that this microstructure has this red, which is 1, this red is 1, and this is the vapor. And initially there was no this colored portion because there was no interface, but now an interface has formed, and because this is the half portion, it has to start grooving here, and you can already see some hint of grooving here. Of course, it is also going to groove at these 2 points, because that is another boundary that we have. So, slowly this is going to develop a groove. So, it is going to have a groove here, it will come, it will have a groove here, it will go, and then it will have a groove here. So, that is what this structure is going to be. You can see already that it is developing the grooves, and here also you can see an hint of a groove. In this projection it does not look very clearly, but after this 100 time steps are run, when the groove is big enough, of course, we will change the projection and look at the grooving, but one can see that what was very flat developed these kind of curved regions to make sure that the grain boundary energy here balances the resolved boundary energies in this direction. Okay. So, that is the primary reason why grain boundary grooving happens, and you can see that the grooves are developing here. Okay. So as you can see, I think now it is much clearer. So we had a straight boundary, and that boundary now has, so in 3D, suppose if you had the structure, so this groove would have been in the third dimension. So it will be like a channel that would have run through. So we can see that, we will see that channel structure by rotating it and looking at the channel structure. So there are analytical solutions about the shape of the groove, and what Rajdeep had shown in his thesis is that this profile that you generate using the phase field model actually matches with the analytical groove profile or groove structure that has been found by Mullins. So all these details are available in Rajdeep's thesis. So we are basically trying to do the calculation from his thesis. So now that the calculation is done, let us take the structure and look at how it looks. Okay. So as you can see, this is the groove. Okay. And this is the other groove, and the composition profile contours clearly show how the groove structure looks like. So in color it's very nicely visible. So one can see that this is the red line, and this is the yellow line, and this is the blue line, etc. So this is basically the grain boundary groove. So you have a solid, this is vapor. This is basically a reflection of the same thing for periodic boundary condition, and in this solid, because this is one grain and this is another grain, the region between the grain, as you can see, develops a groove. So for example, from here it is very clear what the groove is. So it is a groove like that, and here also it is a groove like that. So there is a small dip in the structure, and that is basically the grain boundary groove. So by using such a simple model and rather simple implementation, one can generate structures like this. So to summarize, any given problem which is related to microstructures, one can describe using order parameters, and in terms of those order parameters and their gradients, if we can write the free energy, we can also look at their time evolution. So and that time evolution of microstructures is very important and interesting, because this is what helps us to study many phenomena that happens in materials. There is one more code of this type that can be written, which is, for example, for the solidification scenario. When solidification happens, when the boundary breaks up as a dendritic solid that comes about in an undercooled melt when the solid is growing. So it also involves two order parameters. One is related to energy, so that is like Cahn-Hilliard equation, but typically the evolution equation is written in terms of temperature, and that is not conserved. So that is one equation. The other equation is of course solid liquid conversion. So if you can write this phase transformation, if you can describe this phase transformation microstructure using an order parameter phi, and if you can use the temperature order parameter and then you can couple them appropriately, then you can actually get the solidification problem also studied. So we will use the solidification problem as one of the tutorials to look at how the microstructure evolves during dendritic solidification, and we have not done that as part of this course, because we have been looking at solid phase transformations primarily. The phase field models that are related to solidification are slightly different in their philosophy or in their flavor, as we will see in the next part, in the next lecture. But in terms of numerical implementation and in terms of the way the equations look, they are not very different. So one can do that also, but the theoretical underpinnings are very different. So I am not going to go into those details. That is the reason why I am not doing that problem as part of this course, but as an extra tutorial or exercise, it is a good idea to do that problem also. So So, this brings us sort of to the end of the application section of the course. So, we have looked at many different microstructural features and how they can be modeled using phase field models, and what are the steps involved in developing the model and in doing a numerical implementation. Okay, with a very small computational power, a laptop which runs Octave, we are able to get lots of interesting microstructures, plot them and see them and get a feel for what is happening. So that brings us to the end of this problem, namely grain boundary grooving modeling. So, there are lots of tutorials that are possible in this part of the code. So, for example, the free energy structure, plotting the free energies and looking at it, and plotting the profile of the interface and looking at it and comparing it with the analytical profile. So, there are plenty of things that one can do, and we will do some of it as part of the tutorial, and which will bring us to the end of the course on the applications of phase field modeling. Thank you.